In this video, I'm going to talk about reduction of aldehyde and ketones. Aldehyde and ketone, they are containing carbonyl group in their structure. In both of these compounds, we have a carbonyl group, and oxygen in their carbonyl group has more electronegativity rather than carbon. So oxygen pull electron density away from carbon to the oxygen, and oxygen get partially negative charge and carbon can have partially positive charge. We can rewrite the structure as a resonance form in this way and put single bond between carbon and oxygen, and then oxygen has negative charge and carbon has positive charge. So this positive carbon in aldehyde and ketone is a good site for addition of nucleophile to this compound. We are able to use nucleophile that can reduce our structure like negative hydrogen or hydride ions. There is different reagent can produce negative hydrogen for us. There is two famous reagents, lithium aluminum hydride and sodium borohydride for this conversion. Lithium aluminum hydride is very strong. It can react with aldehyde, ketone, esters, too many different functional groups, so it is not very selective when we want to only convert aldehyde or ketone. Also, perform the reaction with lithium aluminum hydride is a lot harder. We need to have the right solvents and we should control carefully, otherwise we can have accident during the performing of the reaction. Because of that, we are not interested to work with lithium aluminum hydride as much as is possible in the lab. So for this reaction, we are going to use sodium borohydride. That's a lot safer. We can perform it even in the protic solvent, and quenching of the reagent is a lot easier. So what happened during the reaction between sodium borohydride and aldehyde or ketone? Actually, sodium borohydride can produce negative hydrogen. This negative hydrogen can attach to this positive carbon. Then we have this structure. So at the end of reaction, we need to quench our mixture by addition of acid. Normally we are using hydrochloric acid or HCl. Then this negative oxygen will convert to the OH, and the remaining sodium borohydride also can quench with the hydrochloric acid. Then we will have alcohol as a product from aldehyde and ketone. Aldehyde can produce primary alcohol and ketone produce secondary alcohol. For this experiment, I would like to explain performing of this reaction for one aldehyde and one ketone. So one of these compound is benzophenone. This is the structure for benzophenone. And for aldehyde, I'm going to explain how we can perform reduction reaction for trans cinnamaldehyde. Of course, when we react with sodium borohydride, always in the second step we need to add acidic solution, and normally we use HCl. Then this is the product for benzophenone. All we need to do is just converting the ketone functional group to the alcohol. Same for aldehyde. As you can see here, for both of this aldehyde and ketone, sodium borohydride only reduce the carbonyl group. It cannot reduce the double bond here in cinnamaldehyde or the benzene ring. But how we can perform this reaction? We need to have a beaker, 100 milliliter. Inside of this beaker, we should have a magnetic stir bar for stirring the mixture during the reaction. Then we are going to add 2.5 gram benzophenone and also 30 milliliter methanol as a solvent. Then we need to add 0.5 gram sodium borohydride to the mixture, and this mixture should be stirring during the additions. Keep in mind, sodium borohydride is a very reactive reagent, so we need to add slowly with a small portion of that. So we are not supposed to add all 0.5 gram suddenly at one time. We need to divide it to the small portion and add it slowly to the mixture. And we need to check the temperature, and if it's necessary, we need to keep the temperature below 60 Celsius. Because this reaction is exothermic and temperature can increase when we add sodium borohydride. And that's the reason we're not supposed to add it suddenly. So after finishing the addition of sodium borohydride, we need to let mixture stirring for 15 minutes and then transfer all mixture inside of a beaker that's containing crushed ice and 10 milliliter 6 molar hydrochloric acid. After addition, we can see the bubble forms. This bubble is for reaction of acid and sodium borohydride can produce hydrogen gas. After bubble has ceased, we are going to collect the solid by vacuum filtration. And then we may need to leave the solid under vacuum for 10 to 15 minutes to make it completely dry. After that, analysis the product by IR and also by measuring the melting point. Keep in mind, when we want to take IR, we should have IR from the reactant, it means benzophenone, and also from the product. So performing this reaction for benzophenone is easier because our product is solid and it has high melting point, so we can easily filtrate it by vacuum filtration and purify. But if we want to perform the reaction for cinnamaldehyde, the recipe is a little different. Again, we need to have a 100 milliliter beaker. Inside of this beaker, we should have magnetic stir bar. Then we are going to have same amount of compound, 2.5 gram aldehyde, 15 milliliter methanol. We have lower amount of methanol because this compound is more soluble in methanol. So changing the amount of methanol is just depending to the solubility of this compound. It doesn't have effect on the reaction conditions. And again, we have 0.5 gram sodium borohydride. So again, we need to add sodium borohydride slowly to avoid increasing the temperature. Then we need to give 15 minutes time to the reaction. And then we are going to add a small amount of crushed ice into the beaker and start to add 10 milliliter HCl dropwise. When we add HCl, we can see the mixture start to bubbling, and if after finishing this amount of HCl, the bubbling it doesn't finish, we need to add more HCl, maybe 5 milliliter more, and give it also 5 more minutes to make sure this mixture is completely quenched. After that, all of this mixture it transferred to the separatory funnel. So our product it doesn't form solid in this mixture. So we need to extract it from aqueous solution. We are going to extract by 2 portions of 20 milliliter dichloromethane or DCM. So we need to perform this extraction 2 times every time with 20 milliliter. And we know DCM should be at the bottom and aqueous solution stay on top of the DCM. After extraction 2 times with DCM, then we discard aqueous solution. We don't need it anymore. And then we combine organic layer. So we should have 40 milliliter actually organic layer. And then wash this organic layer with 30 milliliter brine. And we know brine is saturated solution of sodium chloride. And when I mention wash the organic layer with brine, it means we need to add brine and organic layer inside of the separatory funnel again and shake it like extraction. Then discard brine and transfer the organic layer inside of a beaker and add approximately 1 gram magnesium sulfate for drying the organic layer. Here we mentioned the amount of the magnesium sulfate, but actually the amount of magnesium sulfate is dependent to the performance of the person in the lab. If we have more water in our organic layer, we should add more magnesium sulfate. And when we add magnesium sulfate to the mixture, if it remains as a powder, it means it is dry. We don't need to add any more. But if the powder shape change and stick to the beaker, it means the system is not dry and we need to add more magnesium sulfate. So after drying the organic layer, we're going to decant the organic layer inside of the round bottom flask. The size for this one should be 100 milliliter and we should weight it. So this flask should be pre-weighted. Then we can measure the mass of product at the end. So after transferring the organic layer inside of this round bottom flask, we are going to use rotary evaporator to evaporate the DCM and obtain our final product. After collecting the product, so we are going to analyze our product by IR and TLC. For performing the TLC, we should have 1 spot from the reactant and 1 spot from the product. The solvent we are going to use is mixture of hexane and ethyl acetate, 2:1, 2 hexane and 1 ethyl acetate. After taking TLC, we should able to answer, do we have product or not? Is it pure? Which one is more polar? We should able to answer this question based on the TLC. If we have more polar compound, normally more polar compound, they show a spot on the lower. So the non-polar compound, they can move faster during the TLC. And also we should measure the RF for reactant and for the product. Thank you for watching this video. To watch more video, please subscribe our YouTube channel.